Alrighty, so here's where we left off from the last one. So here we have, we're going to add up these vectors, and then we're going to take a look at Pythagorean theorem, sorry, projectile motion. So here we need to find our components of vectors A and B individually. So the x and y components for A, the x and y components for B, and then what we're going to do is we're going to add like components together. So the two x components, the x for A and x for B, the y for A and the y for B, and those, when you add them up, will give us the r components, so the x components for r and the y component for r, and then we can work backwards like we did before, where we have our just a right triangle at that point, and we can use Pythagorean theorem, or the modified version of it, to find the magnitude of r, and then use inverse tangent to find the direction of r. So that's basically what this is explaining that we are going to do. And here's the process. So now don't draw that picture just yet because we're going to add on a lot to it. But so step one is to identify the x and y components of the individual, or where the axes are really. But we do want to find those components, and to do that, we are going to use sine and cosine for both ax and ay. You can see here they did go ahead and add in the r x and ry parts, but we're still not going to draw that yet because we're going to add on more here in a minute too. But once we have our components, we combine the like components together, ax and bx, ay and by, to get rx and ry respectively. Once we have those, we have our components, and now we can use the magnitude and direction formulas. So magnitude here and direction here. Now we don't have numbers given on those just yet, so we'll be adding those on here in a minute as well. So here we have some numbers thrown in now. Now I don't know why they give us the direction of r, it should not be there, but we do know that A is 53 meters at 20 degrees, and B is 34 meters at 63 degrees. So now we can use those two things with our trig to find what the components of A and B are. So here is our solution for that situation. So we are going to write some of this down here. So the process, we want to write down the process. So for AX and for BX, so AX is A cosine theta A, so the angle for A specifically. And so that's 53 meters times cosine of 20, which gives us 49.8 meters. BX is B times cosine of theta B, again the angle for B. So that's 34 times cosine of 63, which is 15.4 meters. So now we have the x components of the vectors individually. We can add these up here in a minute. So before we do that, we want to find the y components. So AY is A times sine of theta A, so 53 times sine of 20 degrees now, which is 18.1. BY is 34, or is B times sine of theta B, so 34 times sine of 63, and that gives us 30.3. So for our x's we got before, we add those up, and Rx is AX plus BX, so 49.8 plus 15.4 to get 65.2 meters. Ry is AY plus BY equal to 18.1 plus 30.3 meters to get Ry, which is 48.4 meters. Now that we have those components, we can now work backwards using our trig, a little bit of trig, but our Pythagorean theorem. Which we would square 65.2 plus the square of 48.4, square root that, and gives us 81.2 meters. And then for the direction part, we would use inverse tangent of ry over rx, which is the inverse tangent of 48.4 over 65.2, which gives us the inverse tangent of, they give us the decimal, but really doesn't matter that much. Theta is 36.6 degrees. Now, to give our answer, we typically want to describe that. It's going to be 36.6 degrees north of east, but again, there are ways to describe the angles without having to use the cardinal directions. And in this case, we could just leave it as 36.6 degrees. So this talks more about subtracting the vectors. Again, the same process applies here, even though subtracting them would mean we have to look at the individual components being subtracted away. But it would do the same thing. You can see here we have AX is this long one, BX is this littler one. We're subtracting it away. So we would then get RX as AX minus BX, and same for RY. AY minus BY will give us RY, which would be negative, which makes sense with the drawing here. But that's how that works. So I actually wanted to go back because I thought there was another slide with the picture, but I guess not. So I do want to get this picture on here. This one specifically, because it has more detail. So I'm going to go ahead and put this up here for you. Draw this picture as well. But I'm going to add on to it because I do want to reiterate a few things that are not pictured here. That R is the square root of Rx squared plus Ry squared, and theta is equal to, where this is theta, tangent inverse of Ry over Rx. So all of that you need to draw and write. Let's get back to where we were here. Thankfully not too far away. So now we have this example problem. I gave students in class about 5 minutes to work through this problem. But looking at it here, we have this right triangle. A is 18 meters, B is 25 meters. I had to make sure it was meters. So we're just using Pythagorean theorem here. Because A and B are already in the cardinal directions, so we don't have to do any of the sine and cosine stuff. So it's just 18 squared plus 25 squared in the square root. So our magnitude, R, I have a highlighter up. So there's our magnitude. Then our direction, theta, the inverse tangent of B over A. Which is the 25 over 18. Now, also keep in mind that A should be negative, so if we were adding on something that, like B had a component in the x direction as well, we have to take that negative into account, but we don't have to do that here. So let's do the inverse tangent of 25 over 18. So that negative would go in and play with the A here as well, but because we're going to describe the angle, we don't have to worry about it here. So that is 54.25. And so the way, again, you describe this, A is my east-west direction, so that is heading east. But from that eastern direction, to get to my resultant vector, I have to move north. So my answer is north of, I said east earlier, west is what I meant to say. It's my bad. It's late at night, not feeling perfect, haven't gotten a lot of sleep lately, so there we go. Those are my excuses. All right, so again, these vectors having two dimensions leads us into projectile motion. And it has that same situation happening where those perpendicular components are independent of each other. So here's some definitions for projectiles. So projectile motion is the motion of an object thrown or projected into the air, subject to only gravity, the acceleration of gravity. Now, they define a couple other things here, but I'm going to write them in a bit better way. So projectile is an object thrown into the air. You can say launched into the air or thrown in the air, however you want to get it there. Whatever is in the air is a projectile. And then the trajectory is the path of a projectile. So make sure you write those two down as well. Now it does talk about air resistance as well, but again, it's negligible for us for all cases, so we're not going to really worry about it. But we do need to keep it in mind because it's still there. It's just we're ignoring it for the sake of the math part of it. So here is a terribly drawn picture of a kid kicking a soccer ball at an angle. It's not even lining up with the path of the ball, but it is at least talking about how they reference the components of the displacement versus velocity in this text that we are kind of using. So description of motion, again, here, those pieces stay separated, but acceleration-wise, the only acceleration acting upon it is gravity, and that is only in the vertical direction. So the horizontal direction has a 0 acceleration. There is no acceleration horizontally, but vertically there is, and that's gravity, which is negative 9.8. And it's negative because it either counteracts the motion and points downward, or it points downward and goes along with it. But regardless, gravity points down, so that's why it's negative 9.8. Now, they're going to do something here on the slides that I'm not super fond of, so I'm going to tweak some things, but just be aware that that could happen, or those things could show up. So here are the kinematic equations we already know. We've already used. We already derived some of them, just for your reference to see them again. So we want to actually go through and write these steps down. Steps to analyze projectile motion. First up, step 1, resolve or break the motion into its horizontal and vertical components along the x and y axes. So that usually means breaking things down into the x components using cosine, the y components using sine. Now, for the most part, the only ones we're really going to focus on are velocity, because those things are really going to be what leads us into looking at the displacement and things like that. Step 2. Well, step 2 is coming. So here we have a couple of pictures that represent the motion of a projectile. So on the top, you can see the parabolic shape of the motion. And it actually has the vectors involved there as well. So the main vector, the purple arrow, you can see it decreases as it goes up, increases as it comes down. And the only reason it is decreasing at all is because of the vertical motion. So the orange dotted arrows are the vertical motion, and they shrink as it goes up and grow as it comes back down, because it's decelerating as it goes up and accelerating as it comes back down. And notice at the very top, there is no orange arrow because it is 0 at that exact point. Then there's the blue arrows. The blue arrows are the horizontal, and notice they are all the same length. That is because there is no acceleration in the vertical direction, or the horizontal direction. So that's why all the blue arrows are the same length. And that goes for both pictures. Step 2, treat the motion as 2 independent one-dimensional motions, one horizontal and the other vertical. Now, this is where they do some things I'm not fond of. So I'm going to tweak some of these, but first of all, hold on. You can go ahead and write down the horizontal ones. They are fine. And you can start to write down about the vertical. I'm going to tweak these formulas though. The first one I'm going to change entirely And the last one, with that middle one, make it plus. They mentioned how gravity should be thrown as a negative, and that's why they throw in negatives in here, which is okay, but it also can cause errors later on. So if you don't think about it and you just throw in a negative and A is there and it's plus, and it's already, sorry, if you throw in the negative 9.8 and it's already negative in there, it's going to give you sign errors. So you got to be very, very careful doing things like that. So the first one, I'm going to change it to delta y because that's how we write our displacement. And this is a bit different of a formula that we aren't going to derive, but this is how they have it. V naught y plus Vfy t. Second one, I do want to add an f in there for Vfy, the final. And the last one, again, is delta y, but this time it is our V naught y times time plus 1/2 gt squared. So those are the equations for the vertical side of it that are written in a format that I like better. Now on the AP test, they don't give you these at all. So just be wary of that. You won't see them. Now, there is a couple other things that aren't written here that were on the other slides that we didn't write down, but are important to know. So, for example, Vx is just V naught times cosine of theta, and V naught y is V naught times sine of theta. Those are important things to note whenever you're looking at these because, well, they're not written there. All right, step 3. Solve for the unknowns in the two directions. Pretty straightforward. Now, at this point, you probably are good. You don't usually have to do more than that. Occasionally, you might have to do step 4, but step 4 is not one that is always required. But you might have to recombine things together, the two motions, to find the total displacement of velocity. But again, that's not usually something that's asked. I haven't seen that very often, that it would ask that in general. But that doesn't mean it's not impossible. But for sure, step 3 is more than likely where you're going to end up finding the thing that you're looking for. So here's just an example we're going to talk through. So we have a firework projectile explodes at a high altitude. Specifically, it explodes at its maximum height. So we want to find that maximum height. That's part A. Part B, we want to find out how much time has passed between the launch of the shell and the explosion. And part C, we want to figure out the horizontal displacement of the shell when it explodes. Now they have those things calculated in the picture already for us. But we're going to show how to find those things. Again, we're ignoring air resistance and gravity is negative, so we need to keep those things in mind. So first things first, the height, which means that we are looking for the vertical displacement or vertical position at the maximum height. So they do have a different formula here that we didn't write down earlier. But it is a familiar one to our kinematics. And we know the final position or initial position 0 because it's on the ground. The final velocity is 0 because it reaches its peak. So those things are eliminated here. So there's no v or y naught. There's no vy, which is the final. So we have this one formula that we do know some things about because we know that it is launched at an angle of 70 degrees or 75 degrees. 70 meters per second is the velocity. So we need to use our sine equation for the initial velocity. Once we have that, we're good to go. So they solve it for y, and then they do that. So they do find v naught y is equal to v naught times sine of theta naught, so 70 times sine of 75. It gets them a 67.6 meter per second velocity. So that is the initial velocity. We plug that in, we square it, divide by 2 times 9.8, and we get that the height is 233 meters. And now that we know that, we can find the next portion. Because now we need to figure out what time that is at. And this formula here, this one we did write down earlier, we have the initial velocity, again the final velocity is 0, and we are looking for the time, so we just multiply both sides by 2, divide by the velocity, and we've got 2 times 3, 233, which was the height we got earlier, divided by the velocity, 67.6 meters per second, which gives us a time of 6.9 seconds. So at 233 meters, after a flight of time of 6.9 seconds, the firework explodes. And now we need to figure out how far out it goes. So I'm kind of skipping over the slide because it just talks about formula usage, but it's not going to be one we're going to use for this one because we are now looking at the horizontal side of it, which means really we're just looking at the x equal to x naught plus vxt. So a couple things we know, x naught is 0 because it starts at a position of 0. So x is equal to v naught or vxt. Vx is our initial velocity in the x direction, which is just our velocity in the x direction because they're all the same. So v naught times cosine of theta naught, 70 times cosine of 75 is 18.1 meters per second. So plugging that into this formula, which we now know the time is 6.9 seconds. So 18.1 times 6.9 is 125 meters. So hopefully they set up the stands to watch the fireworks show further than 125 meters away, or debris from the fireworks and ashes, maybe, or not ashes, but sparks may be falling on spectators. Hopefully that's not the case. But that's why we gotta do things like this, so that those things don't happen. So there is an extra formula here that we are going to jot down. I'm going to add on to it. So this one is to find the maximum height of a projectile. So this one is one we could have used on the previous problem, and they got it in the previous problem. But I'm going to go ahead and add in the fact that it should be negative on the top for one. So negative times v naught sine of theta naught squared over 2g. So they got rid of the negative, but remember, when we plug in a negative 9.8, that will get rid of that negative, so you don't have to worry too much about it, but we do want to remember that g needs to be negative 9.8. So if we ignore that fact, then yeah, everything's positive, we don't have to worry about it. So do write that extra equation down as well. So remember, it is important to define where our coordinate system is, because some things it may have options, and it may be easier to set a coordinate up a certain way than a different one to do the calculations later on. So for example, here we have this volcano where the rock is launched out of it, and now we could set the x coordinate to be the top of the volcano or the ground where the rock hits. Doesn't matter either way, but we do need to know that the difference between the height of the volcano and the ground is 20 meters, because that will affect our calculations. So it probably makes it actually easier to set up our x to be at the top of that volcano, just because it is above it, and now we know that that displacement is a negative 20 meters instead. So resolving this two-dimensional motion into its two individual parts means we need to figure that out. So here we know again a few things. Our final position is that in the y anyway is negative 20 meters. Initial velocity is 25 meters per second. Angle it launches at is 35 degrees, so 25 times sine of 35 is 14.3 meters per second. So that's our initial velocity in the y direction. So using this formula here, we end up with a quadratic, unfortunately. So when we simplify it down, we get 4.9 meters per second squared, or I'm going to ignore the units here. 4.9 t squared minus 14.3 t minus 20 is our quadratic. So using quadratic formula, we get that our times are either 3.96 seconds or negative 1.03 seconds. That negative makes no sense, so it's got to be the 3.9 seconds. So that's what this says again. And now that we have that, we can use that to our advantage in the vertical, or the horizontal direction, sorry. Keep in mind that there are components to that velocity. To find that final velocity that hits the ground at, that's at an angle. So we need to bring that back in. And so we need to find our initial velocity in the x direction, which is 25 times cosine of 35, which gives us 20.5 meters per second. So that's our horizontal velocity doesn't change because it's not accelerating. The final velocity in the vertical direction is going to change, and that's why we need to know that amount of time, because we need it here to figure out this final velocity's y direction. And so that's 14.3 meters per second minus 9.8, or really plus 9.8, plus a negative 9.8, times the 3.96 seconds we got earlier, gives us a negative 24.5 meters per second for that velocity. So then we would work backwards using our Pythagorean theorem, giving us 31.9 meters per second, and then inverse tangent to find our direction, which gives us a negative 50.1 degrees. So that's how this problem works out. There's a definition here. The range is the horizontal distance traveled by a projectile. Sorry if you can hear my son coughing in the background. So the things that affect range of a projectile. Velocity, of course, will affect it. The harder or stronger the initial velocity is, the further the object's going to go. It's fairly obvious. But the angle can affect it as well. And so maximum angle is always going to be 75 degrees. Now, not 75, 45, I was reading 75 and said it. But 45 degrees is the maximum angle. But anywhere outside of that 45, so if you go 10 degrees more to 55 and 10 degrees less to 35, those two will end up in the same point as well. And so you can see that here with the 15 and 75. They're both 30 degrees off from 45, and they land in the same point at 128 meters. Granted, the max heights are drastically different, right? But if you're trying to shoot over something, 75 degrees would be better. Trying to shoot under something, 15 degrees would be better. Maybe. So here's another formula. This one doesn't have a special version of it. That one's pretty solid as it is. This is to find range, but keep in mind, it only works if it launches from the same level that it lands. So that previous problem with the volcano, this wouldn't work. So it has to launch from the same ground level, the same altitude that it lands at. Otherwise, you can't use this formula to find that range. Now, an interesting thing to note here, that range is horizontal, and that everything else involved here has to do with sine, which is y, g, gravity, not usually something associated with the horizontal, but interesting of note that these two things happen here after doing some manipulation of formulas to get the range that it moves horizontally.